Okay, in 17.3, what we're looking at is we're looking at how the reactions actually occur when we have chemical reactions. So one thing that we talked about is for chemical reactions to occur, things actually have to touch. So the atoms that are reacting, if we have hydrogen atoms and we want to make hydrogen gas, those hydrogen atoms actually have to come together to bond to make hydrogen molecules. Well, there's more to it than that. So not only do they have to come together, but for a reaction to occur, the atoms or molecules, whichever the case may be, have to come together with enough energy. So in this first example here, the collision is too gentle. Because it's too gentle, the reaction doesn't occur. So we need to have enough energy to produce a chemical reaction. So not having enough energy will prevent a chemical reaction occurring. So not every time, if we have a mixture of compounds, not every collision is going to necessarily produce a positive chemical reaction. Now let's look at the next example here. So one, they need enough energy. Two, notice in this one, it says the reaction doesn't happen because the collision is in poor orientation. So what we need is these two pieces to come together to react, to bond together. But if they're on opposite sides of the molecules in question, they will not come together and they form that bond. And so in this one, we have poor orientation. So we could have not enough energy, we could have poor orientation, but for the chemical reaction to occur, they need to collide with significant enough energy and in the correct orientation for that chemical reaction to happen. So it is important to remember that not every collision is going to produce a chemical reaction. It needs to have one, enough energy, that's probably the most important, enough energy, and two, the correct orientation. Now, there's more that we can do about the enough energy than the correct orientation. Often reactions do need heat or energy added so the reaction occurs. It's kind of difficult sometimes to correct the orientation. Sometimes the catalyst can do that, but normally what we'll do is just raise enough energy so that we're not correcting the orientation, but we're getting more collisions. And the more collisions we have, the better chance that we're going to have a chemical reaction eventually occur. So that's why normally when we see a chemical reaction like this, where we have reactants and we have products, and we see this energy level diagram, and this is an exothermic reaction. So we think, why doesn't it happen? Well, again, the reason it doesn't happen is because it doesn't have enough energy. It needs that appropriate amount of activation energy. It needs to have the atoms collide with sufficient energy for the reaction to actually occur. So not only do not every collision produce a chemical reaction, again, they have to collide with enough energy in the correct orientation, but also reactions aren't always a one-step process. So in this example, it's saying you can have hydrogen gas mixed with iodine as a gas, and they will form in equilibrium with hydrogen iodide as a gas. So this is a chemical reaction, but what it's saying is that this chemical reaction is really not this straightforward. It's not a one-step reaction. These two things do not just collide and stick together and make this. There's multiple steps to this reaction, and these steps are called intermediaries, or intermediates. How about intermediates? We'll call them intermediates. And notice what we have. It has a couple different processes lined out here. The reason why it has different processes lined out is these are theories. This reaction happens so quickly that we don't really know. We can't analyze what the intermediates are, but we can theorize based on reaction rates what our intermediates may be. So notice in the first one, and again, it's a possible mechanism. It is really a theory. We have a theoretical chemistry here. We could say that the iodine splits into iodine atoms. They attack the hydrogen. We get hydrogen iodide that way. So it's a two-step reaction. The overall reaction is the one that we have written here. The other theory that they state is that, well, actually, maybe it splits apart, attaches itself to the hydrogen, and then the other iodine comes in, breaks it apart to make the hydrogen iodide. So these are two possible reaction mechanisms, and a lot of chemical equations that we assume are kind of one-step reactions like this actually have intermediate reactions. And when we look at them, which we'll do more when we get to kinetics, we can, by the rates of the reaction, try to determine which might be, whether it's a one, two, or three-step reaction, and also what the limiting step might be in each of those. Or better called the rate determining step. So one of them normally slows the reaction down, and that's called our rate determining step. So a lot of times, if we have intermediaries, the other way that we know is we might have multiple stages of activation energy, or what's called activated complexes while the reaction occurs. So notice what this is showing here is this is showing a 3-stage energy activation diagram. Why is there 3 stages? Because it's based off of that theory of having 3 different intermediate steps of the overall reaction. So notice the first one here is we have an activated complex where we have hydrogen and the iodine atoms split apart. Our second step, a little bit more energy, we have the hydrogen iodide and another hydrogen atom. They come together. Notice this is one more step of energy before we get down to our actual compound that we make. Now notice overall, we have hydrogen iodine over here. We have hydrogen iodide. Overall, the potential energy goes down, so this would be an exothermic reaction. But notice, this also requires a tremendous amount of activation energy for it to occur. So there's multiple stages of activation energy. And hopefully this makes sense. Notice the one that's probably going to slow the reaction down is going to be this third step. Now, why is that going to be the rate determining step or the slowest step in the reaction? Well, the reason it might be slowest is notice that one is the one that requires the most energy to occur. So we could form these first couple intermediaries rather quickly, but unless we have a big source of energy, we're not going to get over to that third activation energy to form our final products. Okay, so the last thing we want to do here is we want to be able to label some energy level diagrams, which shouldn't be too terribly hard. So first thing we want to do, notice it says we want to label the change in energy or the change in enthalpy for the reaction. Well, let's draw a line across at where the reactant starts. So these would be our reactants. I'm going to label that point. And I'm going to label this point our products. Now it says copy the energy level diagram, label the reactants, the products, we did that, the change in energy. Well, the change in energy itself is right here. This is the change in energy, or again, if it's a chemical reaction, we'll probably call it the change in enthalpy. And notice this potential energy goes up. So this would be an endothermic reaction. We have to put energy into it for the reaction to occur. The products are actually less stable energetically than our reactants. Now notice what else do we have? It says label the activation energy. Well, the activation energy, let's calculate this value too, I believe we should do. So notice from 0 to 50, so this value would be, and let's write the correct value down, would be a positive 50. What are we in? Kilojoules per mole. So our change in enthalpy is a positive 50 kilojoules per mole. Now what do we want to find? The activation energy. Well, the activation energy is going to be between here and here. So notice we have to go up, what would it be? 50 to say maybe 80 if I estimate. So 50 to 80, our activation energy is going to be 30 kilojoules per mole. Now we have to be a little bit careful with the labels though, because what these labels are, this isn't actually the activation energy that they want. This EA is actually what's called the energy of the activated state, or the activated complex. And what that is if we're doing this EA, it's actually that top energy all the way from the reactants. So the energy of our activated state itself is 80. That's the potential energy of our activated state. The other one that it says is the energy of the activated complex. Now this is what we think of more often as the activation energy. And actually that is the one we really want to be worried about more often, because that's the one they're going to ask about, is the activation energy. The activation energy is the difference between this level and the bump that we have to go over for the reaction to occur. So the activation energy is from here up to the top. That's this symbol in this example. Now it says also determine the value of the forward reaction, the reverse, and these. Well, the forward reaction we already did is plus 50. The reverse reaction then has to be the opposite, has to be minus 50 kilojoules per mole. So just like our other energy diagrams, if we go forward, the overall change in energy is plus 50. We've gone from this state to this state. If we go in the reverse, we've gone from products down to reactants. The change in energy is a negative 50.